Okay, we're going to finish up the last part here of organic and then do a little carbs, I think, at that point. So obviously, we talked about last time a couple of oxygen-containing organic groups. So what we have left is really nitrogen-containing groups. And those are really, as we will see, those are our amines and our amides. Our last sort of organic type groups. They both basically have nitrogen as part of their functional group. Um, and they're really based off of a couple other types of organic molecules that we'll talk about. But first, we're going to start with amines. And amines really have the functional group basically NH2, this kind of nitrogen containing group. They are, as we will see, basically sort of a derivative of ammonia. So they are very much based on ammonia, which is NH3. So they are very similar to that ammonia, which is a weak base. And as we'll talk about here, again, amines can actually sort of behave like a base because they do have that sort of group that's present. And that's what we see here. There's our amine sort of group on this particular guy here. Now, amines, as I mentioned, are derivatives of NH3. They have basically a nitrogen containing, at least in most cases, two hydrogens and sometimes more. Um, and they're also attached to a carbon. Um, there are, as we will talk about as well, we can identify amines as much like we could do with carbons and even alcohols and so forth. There are primary amines, secondary amines, and also tertiary amines. And much like pretty much all the other primary, secondary, and tertiary things we talked about, it is how many carbons in this case are directly attached to the nitrogen. So here we're looking at the nitrogen and we're looking at how many carbons are attached there. And as we will see here, again, basically one carbon attached is primary, two carbons secondary, and three carbons is a tertiary. So here is a tertiary amine. This nitrogen is attached to one, two, and three carbons. Here on the bottom left is a secondary amine. It's attached to one and two carbons. And here is a primary amine, which is attached basically to one carbon there on the benzene ring. So amines, very much like alcohols, like carbons, can be classified based on primary, secondary, and tertiary. Once again, here, like we've been talking about, pretty much I do personally count the carbons because it's just easier. But sometimes, again, people will count hydrogens and kind of no hydrogens attached to the nitrogens, say tertiary. If you got like one hydrogen, it is a secondary, and if you got two hydrogens, then it is a primary. So sometimes people count that as well. And here again are some more examples. Nitrogen attached to one carbon, primary. Nitrogen attached to two carbons, two and three carbons, again, tertiary. And once again, you can see kind of two hydrogens, one hydrogen, no hydrogens for our tertiary guy. They all, though, do share the non-bonding lone pair electrons there on the nitrogen. If you remember, NH3, which is ammonia, is a polar molecule. It also has the ability to hydrogen bond, right? Because it is a hydrogen that's attached to a nitrogen, right? Oxygen or fluorine. So in this case, it's attached to a nitrogen. So that does give amines some properties, and as we'll talk about in terms of solubility with water, stuff like that, because it does have the ability to sort of hydrogen bond. All right, so how do we go about sort of naming amines? We're going to kind of go with the common name for amines, and the common name for amines essentially is very much like what we do for ethers as well. We basically go to the nitrogen here instead of the oxygen like we do in ethers, and you basically just want to find the groups that are attached there. So here we have one carbon group, which is a methyl, and then we just simply put amine at the end of it, So that is methylamine for our primary. Here we actually have two methyl groups here. And again, we just name it kind of like normal. This would be dimethyl. And once again, we just put the amine at the end of it. And this is one, two, and three carbon groups that's attached to the nitrogen. So that's going to be your trimethylamine. So this is really, in terms of naming, really a more common way of naming. It is definitely not the IUPAC way of naming, the more formal way, but we'll go with this type of naming, which is pretty straightforward, hopefully. And that's what you can see here. Just like other things where we kind of name them as groups. Thank you. We do put, if there are different groups attached, obviously we go alphabetical order. We also go, by the way, again, alphabetical order regardless of prefix. So that's why on this one here, we have an ethyl group and we have two methyl groups, which gives us dimethyl and an ethyl, alphabetically E before M. So we ignore the di in terms of alphabeticalness there, and we would get an ethyl dimethylamine, and obviously our dimethylamine and ethylamine here. All right, so why don't you take a second here and classify each of these, and then also why don't you give it. Okay, so let's take a look again. In this case, we're going to look at the nitrogen, and what we want to see in terms of classification is how many carbons are directly attached to it. So in this case, it's just one carbon. So this would be a primary amine. Also has a couple of hydrogens, which kind of tells you that as well. If we look at the nitrogen here, it is directly attached to 1, 2, and one more over here makes 3. And that would be a tertiary amine. In the case of naming here, we go to our nitrogen, sort of isolate our nitrogen. Then we basically look for carbon groups attached. And we got basically one right there. And that is a 3 carbon group, which is based off of propane. So that's a propyl and then amine in this case. If we look at our guy on the bottom there, we got a couple of methyl groups happening. So we got a dimethyl. And we got, again, the 2 carbon group there, which is the ethyl. So as we saw on the previous page, E before M here. So that would be ethyl, again, dimethyl. And again, we're just going to put amine at the end of it. Any questions on that there? All right. Now, there are also aromatic amines. Aromatic, right, means that there's a benzene ring in there. And we saw this one when we talked about benzene sort of guys, and that has a historical name known as aniline that has basically an amine group on top of the benzene ring. This again is a primary amine as it's attached to just one carbon here. And again, if we had that with something else attached, this whole thing would give us the base of our name, which is our aniline. Where this guy is located, that carbon would be carbon number 1 on the ring. And then obviously that would get us our 4-bromo aniline. We don't need to, again, give the number where the NH is located there, NH2 is located. Now, this is a little bit different as well, especially when you have sort of secondary or tertiary amines. Now, when we look at this last guy here, this whole thing, once again, is basically our aniline part of the name. But in this case, we also have a methyl group there, which is this guy right there, a methyl. The difference, though, is in this case, and what happens with amines and also amides, as we will see, it's not actually attached to a carbon. And normally we reserve numbers for carbons, like it's on carbon number 1, carbon number 2, carbon number 3. Here it's actually attached to the nitrogen. So with amines and amides, if you see names, you will sometimes see N written. And the N is basically telling you that this methyl group is not attached to a carbon, but it is directly attached to the nitrogen. So instead of saying like 1-methyl or something like that, which would go with a carbon, because this methyl group is attached directly to nitrogen, we just use N instead of a number. And again, the N basically means that it's attached to a nitrogen and not a carbon in this case. By the way, if we had something like this, and maybe 2-methyl groups attached to the nitrogen, just like what we do with carbons, if we have groups attached to multiple locations, we give the number twice or something like that. Here we would do like NN, and this would be dimethyl aniline in this case. Again, the NN represents that we have a methyl group on the nitrogen. They're both attached to the nitrogen. So kind of the same idea there. As we do with numbers in this case. Any questions on that there? All right, here, so let's take a look at the first one. Once again, in terms of classification, we got nitrogen connected to 1, 2, and 3, so that's going to be a tertiary. Again, we just kind of want to isolate the groups here attached to nitrogen, so that is an ethyl group as 2-carbon group, and so is that one. And then we have our 1-carbon methyl group there. So we do have a diethyl methyl amine in this case. Again, alphabetically here, we're going E versus M in terms of looking. Any questions on that one there? Here on this one, this is the nitrogen attached to 1 carbon there and also attached to a carbon there on the benzene ring. So that's going to be actually a secondary. Now, in this case here, this big guy is our aniline, basically. So that's our aniline. Now, here we do have an ethyl group. It is, again, here not attached to a carbon, but actually attached to the nitrogen. So this is where we would use our N-ethyl instead of a number because, again, it's attached to nitrogen and not a carbon in this case. So kind of use numbers for carbons, and in this case, we use N to kind of same idea, but we just don't give a number. Any questions on either of those there? All right, obviously line structure works the same way. Obviously, you do need to write in the nitrogen and how many hydrogens there are. We can't leave it empty again, otherwise it is a methyl group there at the end. And there's our propylamine or ethyl propylamine and our diethyl methylamine. And that is our propyl group there, and that is our ethyl group there. That is our propyl group there, and our 2 ethyls and our 1 methyl group there. Now, solubility of amines, because they have the ability to hydrogen bond, they are pretty much soluble in water, much like most organic things. As long as it's like 6 or less carbons, you're going to be pretty good. Again, because they do have the ability to hydrogen bond. That's primary and secondary. Tertiary amines cannot hydrogen bond. The reason for that is when we look at the nitrogen, it has no hydrogen. So no hydrogen means that in a tertiary amine, it cannot hydrogen bond, obviously, with water, for example. But primary and secondaries, primary's got a couple of hydrogens, and secondary's got 1 hydrogen attached to that nitrogen. So that allows them the ability to hydrogen bond. Again, upwards of 5, 6 or so, you're going to be good in terms of solubility in water. As you get bigger, as we've talked about, it diminishes its ability to be soluble. Because amines do contain that NH bond, they will hydrogen bond, and again, that tertiary cannot do that, and because it has no hydrogen. So if amines are more than 6 carbons, the effect of hydrogen bond is diminished, and basically the nonpolar part of it makes it pretty much not going to be soluble, as you will see with a primary or secondary. The nonpolar hydrocarbon chain decreases the solubility. So just like anything else, even if you did have an amine that's got a couple of hydrogens, if you build out, very badly drawn there, a bunch of carbons and hydrogens and a big nonpolar part of it, it's just going to kind of get in the way and it's still not going to allow it to hydrogen bond well. All right, so take a moment here. Which of the following should be soluble in water? All right, so first one's an amine. As we see the functional group there, it is a primary amine. It's got a couple of hydrogens, so that is going to be good to hydrogen bond there with water. I just got a couple of hydrogens to do so. Here we also have an amine. This is a secondary amine as it's attached to a couple of carbons, but it still has a hydrogen. So that one should be good as well. Bottom guy should not be good because that's an alkane, right? It's not a amine at all. There's no nitrogen in that thing. That guy's going to use dispersion forces, and again, water is going to use hydrogen bonding, so that's not going to mix really well at all. Any questions on that there? So as I mentioned, since amines are really based off of ammonia, which is a weak base, it's not surprising that they can also act as a weak base. And again, the same sort of Bronsted-Lowry definition of a base. So here in ammonia, it's going to accept the H plus, which is definition of a base, makes NH4 plus and OH minus. Here, methylamine will basically do the same thing. It will accept the H plus from water. Water here would be acting as the acid, and our methylamine would be acting as the base. That's going to put on an H plus over here. So we do adjust the charge like we talked about when we're doing Bronsted-Lowry, and we're left with hydroxide. Both of these produce hydroxide, which is why these things are really basic, because in solution they have the ability, obviously, to produce hydroxide, which would make that solution basic. Now, neutralization forms of amine salts. Amine salts form when amines react in a neutralization reaction, say with citric acid. For example, here amines are those responsible for the odor that you smell in fish, and they are neutralized by acid, so that's why they throw on there some lemon or orange or something like that, some type of citrus on it there to help with it. In this neutralization reaction, because it is a base, it just does the normal acid-base reaction. So here our amine is going to act as the base. Here we got our acid, which is obviously our acid. And it basically will make a salt in this case. A salt is still an ionic compound. This guy is still going to send over the H plus to our base. That's going to cause our base there to gain an H plus. If you get rid of the H there, conjugate partner there is the Cl minus, positive, negative ionic compound known as a salt. In this case, it's referred to as an amine salt because it comes from an amine. Same thing here, again, going to send the H plus over. That is going to give me an extra H and a plus. That H goes away, gives me the Cl minus on this side here. You will not need to obviously name the salts or anything like that. Properties of sea salts, they're used sometimes in drugs. They're also solids at room temperature. They're usually odorless and usually soluble in water because ultimately they're an ionic compound, and ionic compounds are usually soluble in water and no problem. Some other properties of these ammonium salts, it's used in as the active ingredient in some of these decongestions like Sudafed and Benadryl. Also narcotics like cocaine. We have amines, ammonium salts there, as you can see right there. And also alkaloids. These are physiological active compounds in plants that contain nitrogen, like nicotine here. So nicotine again, we have our amine sort of property of it there. That is a tertiary amine right there. Nitrogen attached to 3 carbons in that particular case. Caffeine as well, everybody's favorite amine, perhaps, if you like coffee, I suppose. Also an amine going on in that situation as well, all the way around there. Lots of nitrogens happening there. Morphine as well. There's our amine group there on morphine and codeine. All right, so why don't you All right. So in this case, kind of like the ethers that we drew, I would start with the nitrogen in this case because we know we need to have it. So methylpropylamine tells me to be a straight chain amine. So I'm just going to start with the nitrogen. And really at that point, you just got to draw the groups on whichever side of the nitrogen you like. So propyl is 3 carbons and methyl is 1. We'll put in our hydrogens kind of like normal here. The other thing that you do need to think about though is the nitrogen, and it will also in some cases need a hydrogen there. Otherwise, it'll be a little short of some bonds. Although a lot of times not drawn, again, there's the non-bonding electrons there on the nitrogen, which gives it 8 electrons that it needs. This is a secondary amine, which means it should have 1 hydrogen in this case. So that's how you kind of know. Yeah. Perfectly fine. Yeah, you can put them any way you want. So you go up, down if you want. You can go up to the right, up to the left. It doesn't really matter. No. Any other questions? Yeah.
CH3, CH2, CH3, and then on top we put CH3, and then next to we put NH2.
That would be incorrect if you did that. So if you have the methyl attached to the kind of propyl group, then that would be incorrect. It needs to be attached to the nitrogen in that case, yeah. And then you would also, in that case, have too many hydrogens because it should only have 1 because it's a secondary amine in this case. Other questions? All right, so aniline is really our benzene ring. And it's got a nitrogen happening there. By the way, here, that is 2-chloral, and that's a number, not an N, which that means that number is attached to a carbon. We know where the nitrogen is in the ring should be carbon number 1, and it really is your option. You could go left, you could go right. I'm going to go right and call this number 2, and that would be my chlorine. Once again, here we do need to fix up our nitrogen there. It has basically 1 bond and a couple of electrons. So in this case, since it's a primary, it would need a couple of hydrogens on it. Or you could just write NH2 if you want up or on top without drawing it out. What's the question? No? Okay. Yeah, you could write NH2 as well on top, yeah. I'll be honest with you, I'm okay if you leave off the dots or if you don't put the dots. I would say probably a lot of times they don't put the dots, kind of like what they do in with like oxygen. They oftentimes leave those dots off. They are there just so you know, and that's how it gets stayed. But if you leave it off, it's not super critical for our purposes here. It would, yeah. So technically, this guy would have dots and that guy would have dots, yeah. And it gets nitrogen to the octet rule, basically, it'd have 8 electrons around it. But again, a lot of times in the organic part of it, they sometimes will leave those off, especially in this type of level of a class. They'll sometimes leave them off. Question? If you put NH2, it would be because for A you're talking, right? Yeah. Yeah, it would be wrong because technically that nitrogen where I circled here, it actually has some electrons there. So if you put an extra hydrogen, that nitrogen now has like 10 electrons, right? More than the octet rule, it's too many. So that's why it really doesn't have that hydrogen there. It does because it's really based off of ammonia, which if you draw ammonia, it's really is this, yeah. So it's basically carrying that nitrogen with the two lone pairs on them and stuff. Yeah. Yeah. Yes, to draw the H. You you don't have to in this case. You could have done this if this is what you're asking. If you done this and did something like this, that would have been okay as well. If you did something like that. Yeah. Other questions? Okay. All right. So those are amines. Now to the final organic group of the season here, which is amides. Amides are basically nitrogen-containing groups that kind of looks like a carboxylic acid, except it doesn't have an extra oxygen. It's attached to a nitrogen. So the functional group here for an amide is this guy. And it's similar to a carboxylic acid because, frankly, that's how you make it with a carboxylic acid. And you make it with an amine. So you slap together basically a carboxylic acid and amine. Maybe not surprising to you, you take out water to do that. You take out water and slap them together, and you get an amide here. And that's the amide group right there. And that is where it's put together. And that basically is your amide sort of group. So Tylenol, which is acetaminophen, is an amide, and that's what you see right there. That's acetaminophen in your Tylenol there. So as I mentioned before, these are basically from a carboxylic acid and basically either an amine or even ammonia as well can do it, but some type of amine type group or ammonia derivative. They come together, and it's the same idea here. If you turn this guy back around this way and draw it the other way and kind of draw out the nitrogens, you take out water basically. And then they get just squished together, basically. So you take out the OH from the carboxylic acid, you take out one of the hydrogens from the amine, that takes out water, and then whatever's left, kind of like what we do in a esterification reaction, just squeeze them together and you'll get your amide type group that happens there. And this is what's known as preparation of amide is basically that. Again, here's ammonia. We're going to take out water, and that's where it comes here. And then really nothing else changes, just like in an ester. You got your CH3, your CH3, your CH2, your CH2, your carbon oxygen double bond. Skipping in the water part, you got your nitrogen, hydrogen, and your hydrogen. So everything stays the same. You just squish them together, basically. Same idea over here, propanoic acid. We take out our water, and then we just put them together. CH3, CH3, CH2, CH2, carbon oxygen double bond, nitrogen, hydrogen, and CH3 basically put together. The importance is to understand that is the connection there. A carbon to a nitrogen connection is where they come together when you put it and you kind of put them together. Again, going where the carbon oxygen double bond is away from the nitrogen is your carboxylic acid part, and going towards the nitrogen is basically your amine part in that case. Any questions on that there? All right. So here, if we were going to do this again, just like we did with the esterification, sometimes it's easier to turn this guy around and kind of line up the nitrogen because that's where the connection is going to occur. So if we did that, we could move our nitrogen. I'll just draw the hydrogens kind of this way. And then we have our CH3. Once again, we're going to take out water, which is right there. And nothing else changes. So our carboxylic acid here will still look the same. We are now going to connect to our nitrogen because that's going to give us our amide connection, and everything stays the same on the other side. So again, we're just going to take out the OH and one of the hydrogens and then put them together there to make our amide connection. Any questions on that one there? Naming amides, nobody wants to do that at this point in time, right? So Don't worry about that, I suppose. Still don't worry about it. Still don't worry about it. I'm still not worrying. I'm still not worrying. After looking at those names, I'm not worrying about it at that point. All right, let's talk a little bit about some amides and health. So you don't have to name them, obviously. Urea is an amide, and again, that is our whichever way you want to go, basically. That is our amide part there, and again, the connection there between those two. Some barbiturates as well are also amides, and again, there we go, some amide connection there. Aspirin substitutes as well, and here would be an amide, again, carbon, nitrogen, double bonded oxygen, and hydrogen. Amides undergo basically two reactions. They undergo acid hydrolysis and also base hydrolysis. And again, these are really, as you can think about it, breaking them apart. So kind of similar to what we saw with esters here, we could break these guys apart using an acid, and that produces a carboxylic acid and a salt. So for example, here, if we take a peek at this guy, here's our amide, and we're going to use water and an acid. And to do so, what's going to happen is where it comes together is exactly where it's going to break apart. In this particular case, we will get back a carboxylic acid completely. So we'll kind of use up an OH, if you will. And we will add on hydrogens there. And we got a couple of hydrogens to go with our one that was left over. So a couple of hydrogens and one left over. And then obviously we have a chloride from the acid as well. So we don't get an amine back, but we do get an amine salt in this particular case. And but we do get the carboxylic acid back. So if you do the acidic hydrolysis of an amide, a carboxylic acid, and an ammonium salt. If you do the basic, where we're using sodium hydroxide here, it's sort of the opposite. You actually get the amine back, and you don't get the carboxylic acid back. You get a carboxylic acid salt. Again, you could think of it like base gives you back the base, which is an amine is a base. So that's the one that you get back when you do that. However you want to look at it, you could break it apart right there. This guy's going to end up over here, and we borrow an O, an H there, and we pop one of those guys on, and we get basically our amine back. What's left from our sodium hydroxide is kind of what we saw. We got a negative oxygen and a positive sodium, and that gets attached to our carboxylic acid side, which is here. And we get, again, a salt here. We don't get the carboxylic acid back. So a good way to remember this is if you do the acid hydrolysis of an amide, acid, you get back the acid. If you do a base hydrolysis of it, you get back the base, which is the amine in this case, completed, basically. Any questions on those two? All right. So again, here, if we look, this is the base hydrolysis. Whoa, come here. And up this way. There we go. And once again, we're going to break it there. And that H is going to give us back the base part, which is the amine completed. And once again, what is left over, the oxygen is going to connect in there to the carbon to make our carboxylic acid salt, which is basically what happens right there. So again, the base gives you back the amine, which is a base. Draw these structures. Since we're not naming it, nobody wants to draw. All right, so for amines, you do need to know how to name, you need to know how to classify them and draw them. You do need for amides, you need to know the functional group and those couple of reactions. Other than that, that's good, I think. Yeah. Any questions on any of that? All right, that is organicness. Let's go. We're going to go backwards, as we talked about, back to 13. And just in time for the holidays here, we're going to talk about bread and all the good stuff, right? We're going to talk about all those good carbs that might be on the table come Thursday or whatever. So we're going to talk about carbohydrates here. A reminder that last week or so, I think I posted, again, the recorded lecture for 15 and 16, which is just an hour long for both chapters. And again, whatever's in that recording is what you're responsible for the final. Obviously, whatever we talk about here, we'll be responsible for the final. So let's get into carbohydrates. It's saying hello. Those are hands. That's a left hand, right hand. But that has to do with what is referred to as chiral compounds. And chiral compounds are compounds that basically have the same number of atoms, but they are arranged differently in space. And they have one or more what is referred to as a chiral carbon. And a chiral carbon is a carbon that has directly attached to it four different groups. So if you have a carbon that has directly attached to it four different things, that's referred to as being a chiral carbon, and that guy would be chiral molecule in that case. What's the deal with chiral compounds? Well, chiral compounds are if you take a chiral compound and you stick it in front of a mirror and you take the mirror image out and you try to superimpose the mirror image on the original guy that's standing in front of the mirror, they will not match. And that is why the hands are there, because if you put this hand up to the mirror, you get this hand staring back at you, yes? And if you take this hand out of the mirror carefully, you could rotate that hand as much as you like, you'll never get it to match. You could put it this way, thumbs match, but palm up, palm down. That doesn't work, right? You could twist it this way. That's not going to work, right? Don't hurt yourself while you're doing this. But you could do as much rotation as you want. You'll never get the mirror image to superimpose correctly in all locations as the original guy. And that's what you see with your hands again. Even though it may appear like it will, palm up and palm down is different and that type of stuff. So they'll never match. There'll always be something that is off in a chiral compound if you try to rotate it and get everything to match up. Now, here's an example of that. Here we have a carbon in the middle, which is the black circle here. That's a carbon. And attached to that carbon directly is a hydrogen, a chlorine, an iodine, and a bromine. And that is four different groups attached to that carbon. So that carbon in the middle is considered chiral. And that means if we put it up to a mirror, it's going to reflect like so with this guy in the back. And if we take this guy out of it and we take it to our original guy and we start rotating it, we will never be able to get it to sit correctly. This is something very hard to visualize because you look at it and go, can I just rotate? It should just flop right. But again, you got to remember there's a 3-dimension of how those bonds are, and something will always be off. As you could kind of see over here, you could rotate and maybe get a couple of them to match up, but these guys are going to end up being on the wrong sides and they're not going to match up and stuff like that. So that's the idea of a chiral compound. Mirror images that do not superimpose on one another is what is known as chiral. Different than that is what is referred to as being achiral. Achiral are mirror images that do superimpose on each other. So this would be something that has not four things attached to that carbon. So not four different things attached to the carbon. So in this case, because we have two bromines attached to the same carbon, this makes it achiral. And because of those two bromines, what it actually does when you take the mirror images, you have a better chance of rotating this in a way where now you got two things that are the same. They're going to actually match up in this case. And you can take the mirror image with a little bit of rotation and they will fit perfectly right on top of each other. Here are some everyday examples of chiral and achiral type of things. Gloves there are chiral. Golf club, soccer ball is achiral. A glass is achiral, and your shoes there are chiral. And right-handed scissors are chiral as well. All right, so take a moment here for each of these. Are these chiral or achiral type of compounds? Chiral. So this carbon has a chlorine, which is different than a CH3. That's different than a hydrogen. That's different than an ethyl group. So that is four different things attached to that carbon in the middle, which would make this chiral. That means that that mirror image will not superimpose, right? By the way, if you're thinking about these carbons, what about them? They are not chiral because each one contains multiple hydrogens, right? So They obviously don't have 4 different things attached to them as they both have multiple hydrogens. Here we look at this carbon here. We got this guy, which is different than the Cl. That's a hydrogen that's different, but that's 2 hydrogens. So that is not 4 groups that are different on that carbon. And that would then make this achiral, which means if you put that up to a mirror, you can pull out the mirror image, the rotation, get it to fit perfectly on top of the original structure. Here we got that CH3 different than chloride, different than hydrogen, different than bromine. So that is 4 different groups, and that would give you a chiral compound. Any questions on any of those, or how to identify a chiral carbon, sometimes referred to? All right, they agree, so that's good. Now, Fisher projections are basically 2-dimensional drawings to represent basically 3 dimensions of the molecule. What goes up on top is the most oxidized group. We use vertical lines in place of dashes for bonds that go behind the paper, if you will. And we sometimes use dashes to indicate that it's going backwards out behind the paper. We use horizontal lines and we use wedges sometimes to indicate that it's coming out of the paper in the forwardness. You're not going to have to draw too much of 3-dimensionalness of things, but that's sometimes what things are used for. Again, dashes kind of indicate it's going behind the paper, and wedges kind of coming out the front of the paper to try to indicate that 3 dimensions here. Once again, also with carbohydrates, very commonly, that's how carbons are sort of drawn, where they intersect and stuff are carbon. So they'll sometimes do that. So that's what we see here. Right here is a carbon. And on this case, we have this group above the carbon, which is different than the hydrogen. And that's different than the OH. And that's different than all this guy here. And that's what makes that a chiral carbon in that particular case. Same guy on this right-hand side, that's where the carbon would be. And again, 1 group, 2 groups, 3 groups, and that whole thing considers sort of a group for that particular carbon. And that is 4 different things attached to it, which gives it a chiral carbon. Now, that also brings us to some notations of D and L. D basically means right, and L means left. And when we have carbohydrates, for example, we sometimes indicate them as either the D form or the L form of it. And what it has to do with is where the last OH group is located on the furthest chirocarbon from your oxidized group. What is our oxidized group? It's our carbon-oxygen double bond. So we're looking for the furthest down from that carbon that is chiral and where the OH group is located. In this case, this guy is a chiral carbon. This guy is not a chiral carbon, again, because it has 2 hydrogens attached to it, right? So that's not 4 different groups. So that is our last chiral carbon from our oxidized group there. And there our OH group is on the left-hand side, and that gives us L-glyceraldehyde. Same thing here, that is our last chiral carbon away from that top group there, where the carbon-oxygen double bond is located, and here our OH groups on the right-hand side. So that would be our D anomer there, our structure. When you're looking for in carbohydrates, where the last chirocarbon is located, and by the way, there could be multiple chirocarbons in, say, a carbohydrate, or you could have 1, or you could have 2, or you could have 3. I would say not 100% of the time, but pretty darn close. If you just go 1 carbon up from that guy, you're probably looking at the last chirocarbon. There's usually a CH2OH group on the bottom. And if you kind of usually go 1 above that, that is a lot of times your last chirocarbon. Again, not 100% of the time. It's possible it's not, but in a lot of cases, that is where you can find it. All right, so take a moment here and indicate whether each of these Mirror images that cannot be superimposed. It's like a double negative, I think, there. So we're looking at which one cannot be superimposed. All right, so looking at this, perhaps what you want to figure out is it chiral or achiral? And then you'll know, can you superimpose it or not, basically. So this guy seems like a pretty prominent carbon there. That is one group that is different from this group, that is different from this group, and that is different from that group. That would be a chiral carbon, and that would be a chiral compound. And as we know, if we stick our mirror right there, chiral compounds, mirror images are non-superimposable. So I guess to answer the question, yes, this guy is non-superimposable. Yes. Any questions on that one there? Coming down here, we got our carbon. That is a group that's different than this group, that's different than this group, but this and this are the same. That means that that is actually achiral. And all of the other carbon there has 3 hydrogens attached to it, so that definitely is achiral as well, not chiral. Achiral, guys, means that you can take that mirror image and it will superimpose. So I guess to answer the question, this question, no, this one can actually be superimposed, not superimposed. Double negative, I suppose, yes. Any questions on that there? All right. So let's talk a little bit about carbohydrates. Carbohydrates are a major source of energy in our diet. They contain basically carbons, hydrogens, and oxygens. They're sometimes referred to as saccharides or sugars, and all the good stuff there in the picture. We produce carbohydrates through photosynthesis in plants, and again, this nice little cycle here, carbohydrates, respiration, a little energy there from the sun. Such as glucose, we use glucose, right, through glycolysis, right, for a little bit of energy. We store it up there so we can use it in gluconeogenesis in case we need to break it back down and use it for energy. They are oxidized in living cells to produce CO2 and water. And again, a nice little circle there, products there of carbohydrates. Now, there's different types of carbohydrates we're going to talk about. There are monosaccharides. Monosaccharides are the simplest carbohydrates. Disaccharides, like the name implies, di is 2, so that basically is where you stick 2 monosaccharides together. Not surprisingly enough, to do that, you're going to take water out. A lot of these ending chapters just take water out and put everybody together, and you'll be in a good shape in a lot of cases. And there's also polysaccharides, which basically is just a bunch of sugars basically put together, all put together by taking out waters and sticking everybody together. So monosaccharides will not go through hydrolysis because there's nothing to break apart. There's just one. Disaccharides, if you want to break them apart, you can add some water. And polysaccharides, you can add a bunch of waters and it'll break them apart. And again, that's because, as we'll see, we basically take water out to put them together. So if you want to break the disaccharide or polysaccharide back, you got to just throw water back in basically to do so. So let's start with monosaccharides. Monosaccharides consist of usually either 3 or 6 carbons. And they typically have a carbonyl group. So remember that the carbonyl group is that carbonyl carbon, and that is the carbonyl group. It is a polar group with the oxygen being more negative, the carbon being more positive. And in these carbohydrates, we have our same organic groups basically up there at top. We have an aldehyde group up on top, or we could have a ketone type group. And it really is the same thing as we see in organic chemistry. And these are what are referred to as the most oxidized groups, which usually go on the top of the carbohydrate monosaccharide. And they usually will contain several hydroxide groups, and that is our OH groups, right? So they'll usually contain a bunch of those guys on there. Now, one classification of monosaccharides is what are known as aldoses. And aldoses sound like aldehydes, and that's because they have the aldehyde group on them. So if you have a monosaccharide that contains basically the same aldehyde group we saw in organic chemistry, that carbohydrate is sometimes referred to as an aldose because of that. We also classify carbohydrates based on how many carbons it contains. And that is all the carbons here. So that's 1 carbon, 2 carbons, 3 carbons, and 4 carbons. So this guy would be a tetrose. Tetra meaning 4. So tetrose is 4 carbons. Triose is 3 carbons. Pentose is 5 carbons. And hexose is 6 carbons in this particular case. So if we look at the other sort of classification of a monosaccharide, these are what are referred to as ketoses. And ketoses, much like the name sort of implies, they are the ones that contain a ketone group. So remember that for a ketone group, you do need at least 3 carbons in a row with the carbon-oxygen double bond there in the middle. And that is what we see right here. That is 3 carbons in a row with the carbon-oxygen double bond happening in that case. And we also could classify this based on how many carbons it has. 1, 2, 3, 4, 5, and 6. So this would be a hexose, like hexane, 6 carbons. Pentose, like pentane, right? 5 carbons. Tetrose is 4, like tetra. And again, tri for 3. Just like in organic chemistry, you will never find the carbonyl carbon there at the end because you need the 3 carbons in a row. And just like in organic chemistry, when we look at an aldose, you will always find it at the end because it still has that hydrogen. So that guy will always be at the end of your carbohydrate at the very top if it's an aldose. If it is a ketose, it will be still towards the top, but where the carbon-oxygen double bond's located will usually be second in from the top, again, because it needs that 3 carbon run. Any questions on that? All right, so take a moment there and identify this as a aldo, a keto, tetrose, pentose. Heck, let's do L and D, why not? And also, how many? All right, so let's take a look. So first off here on A, I see a aldehyde group, which would tell me that this is an aldose, right? In this case. So this would be an aldo as we have basically the aldehyde group. If I come over to the guy on the right there, which is B, I got me a 3 carbon run with a carbon oxygen double bond in the middle. So that is a ketone group. Which would mean that this guy is a keto there, right? First off, any questions on those there? We can just count up the carbons here to see what it is. We'll go to our guy here on the left. We got 1, 2, 3, 4, 5, and 6. So this would be an aldo hexose. Here on the right, we have 1, 2, 3, 4, 5. So that's going to be a pentose in this case. Any questions on that there? Now that brings us to how many chiral carbons do these guys have? So let's see. Well, we'll start on the guy on the right. We'll start with this carbon. Is that one chiral? That one is chiral. You got that group, this group, this group. And you basically have this entire thing considered a group underneath it. So that's 1. Now, if we look at the guy underneath it, is this one chiral? This one is also chiral because this entire thing now becomes a group, which is different than that one, and this entire thing here. So that would be chiral as well. Yeah. Continuing down here. So we have that guy there. This one also chiral because that entire thing is considered a group. That's a group. That's a group. And this entire thing below it is considered a group, which is different than any of those other things. So that is 3 there. Very colorful so far. And lastly here, good thing we only have one more, I think. That is also going to be chiral again, because now this entire thing is a group. That's a group. That's a group. And that's a group. And that is 4 different things in this case. So this guy's got 4 chiral carbons in this particular case. So as I was mentioning before, definitely can have more than 1 chiral carbon, say in a carbohydrate. Now, when we look at this, what we're looking for to determine L or D is the very last chiral carbon from the carbon-oxygen double bond, basically. Guess I could have boxed that guy. And that would be that guy right there. And simply put here, our OH group looks like it's on the right. So that's like a D situation happening in that particular case. Any questions on that one there? One on the right has how many chiral carbons? Does have 2. This would be 1, and this would be 1. Yeah. And in this case, this would also be D, as that is the last OH on the last chiral carbon, furthest from the carbon oxygen double bond. Any questions on any of those there? All right. Then let's continue on here. So let's talk a little bit about the structures of monosaccharides. As I mentioned before, we can do Fisher projections, and we do put the most oxidized group on top. So that's going to be your aldose group or your ketone. It's going to go up there on top. As I mentioned before, we show chirocarbons as intersecting vertical lines there. So once again, that is a carbon, and that is a carbon, and that is a carbon there. So this guy's got 3. And once again, that guy in the middle there is a chirocarbon, as again, it has the 4 different groups that we saw earlier, 1, 2, 3, and 4. OH on the left there, making it L. Yeah, that's what it's about. All right, so here's some examples of some monosaccharides, D and L isomers of them. They just put a little star on this slide. It's a good one to know. You may need to know the structures of these, not necessarily draw them, but be able to recognize them as glucose, ribose, and galactose. Yeah. All right, if they're provided to you, be able to recognize them. So this glucose is a aldose. It is a 6 carbon, 1, 2, 3, 4, 5, and 6 hexose. And in this particular case, it is D, as that is our last chiral carbon. As I mentioned before, not 100% of the time, but usually you could just kind of roll right above that guy there and probably find your last chiral carbon pretty quickly. Here is ribose, which also is an aldose because it has a aldehyde group, has 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So that is a pentose. And once again, rolling back to our last carbon there, which our OH group is located. And L-galactose here, also an aldose. 1, 2, 3, 4, 5, and 6. Here, the OH group's on the left-hand side on our last chiral carbon, and that gives us a L isomer in this particular case. So again, D and L determined last chiral carbon furthest away from the carbon-oxygen double bond. All right, so take a moment. All right, so looking at this, again, we have a chirocarbon here, here, and here, with this being our last chirocarbon. This not a chirocarbon, again, because it has the 2 hydrogens attached to it. And again, as you can see, 1 up from there is pretty good. That looks like a left-hand situation there, so that's going to be an L. This is a chirocarbon. That is a chirocarbon. And again, we'd see our OH group on the left. And this would be a chirocarbon, chirocarbon, and chirocarbon. And here we see it on the right, or R, D, maybe. It's like R, yeah. Any questions on that there? Okay. All right. So let's talk a little about each of some of these monosaccharides. D-glucose is found in fruits, corn, syrup, and honey. As we saw there, it's an aldose, hexose, has the form of C6H12O6. It is known as blood sugar in the body. Monosaccharide in polymers of starch, cellulose, and glycogen, as we'll talk about a little later on in this chapter. But again, this is D-glucose with our OH group there on our right, and our last chirocarbon that is present. Obviously, we measure our blood glucose levels, normal 70 to 90. And you can take obviously a blood test and they'll run your glucose there. Usually you want to maybe fast before you do that and not have the chocolate chip cookie right before you do it, I suppose. Your sugar just jumps, I suppose. But you can have normal, and then obviously if you have hyperglycemia, then obviously you have a higher amount of blood glucose. If you have hypoglycemic, then you have lower, hypo means lower blood glucose in your system. Now, fructose, which is one of those ones you do need to know as well, in addition to obviously glucose there, it's actually a ketose, as we see. And again, that's our 3-carbon run there. It is the sweetest carbohydrates found in fruit, juices, and honey. In the body, it will actually convert into glucose. Galactose, which was on that slide as well that I said you should probably be familiar with. Galactose is also a aldose, also a hexose, very similar to glucose. It's obtained from lactose, which is a disaccharide. It's not found free in nature, so it's usually tied up there with another monosaccharide to make lactose. It is similar in structure to glucose, except that on carbon number 4, we have the OH group is a little bit different. By the way, when we are numbering carbons, are looking at carbohydrates and trying to figure out what carbon's what, just like in organic chemistry, the functional group gets the priority. So that would be considered carbon number 1. That would be considered carbon number 2, 3, 4, 5, and 6. So very similar to organic chemistry, wherever that carbon oxygen double bond should be to the top and have the lower number. It will not always be 1. Obviously, in the case of a ketose, that carbon oxygen double bond will be really carbon number 2, and there'll be a carbon before it as well. All right, we're not going to draw that there, so don't worry about that drawing. So let's talk though a little about something we will be drawing, which is cyclic structures of monosaccharides. So monosaccharides can kind of say in the straight form, if you will, but they can also kind of close up on each other and make a ring structure and a cyclic structure. And really, the type of cyclic structures that we see in carbohydrates is really similar to the ones that we see in organic chemistry. So you either have a kind of like a cyclohexane ring, or you have like an organic chemistry, a cyclopentane ring. The difference though is when this monosaccharide kind of closes up on itself, because it has a bunch of OHs, we actually insert a oxygen in place of one of those carbons in those rings. And what that gives us is, in the case of like the cyclohexane ring, we actually only have 5 carbons in this ring. 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5. And unlike in cyclopentane, where we have 5 carbons, because of that oxygen that gets inserted, we actually only have 4 carbons, 1 carbon, 2 carbons, 3 carbons, and 4 carbons. So Cyclic structures will either be these sort of 5 or 6 carbon rings, but really they're 4 and 5 carbon rings because they have that oxygen in there. What typically happens to close it up is pretty much wherever the kind of carbon oxygen double bond is located. And a lot of times, if it's a hexose, like carbon number 5, that carbon will come in and those guys will come together basically to make the ring structure. So that is what will close up the ring and make that structure. Now, these are what are referred to as stable cyclic hemiacetals. If you remember, hemiacetals are those guys that have a carbon and directly attached to that carbon. We have like a hydrogen, a OH, and an oxygen carbon group. So that is sort of what's going on here. And these guys, they make these cyclic hemiacetals. For hexoses, the hydroxide on carbon number 5 reacts with the aldose and the ketose type group. The cyclic guy that we form is a diisomer where the CH2OH basically ends up on top. So when you do these, if you remember, when we look at these carbohydrates at the bottom, typically is this guy, that's CH2OH. And where they end up on these rings is always to the left of the oxygen, not attached in the ring, but attached to that carbon right there. Same thing with our other group there. This is where we typically will see that kind of last guy end up kind of off the ring, attached to the left there of where the oxygen is in the particular ring. So how can we do this? Well, let's talk about how we could go from sort of the straight structure into this cyclic structure. So let's just do this here. Let's go. I'll just make up a fake one here. We'll do OH. And we'll do OH. Do OH. And we'll do, why not? We'll do OH over here. Actually, no, I'll move that OH to their side. Why not? I'll put it over here. All right, so this is our monosaccharide, and we basically want to turn this into a cyclic structure. So there's a couple things we want to think about, which is in this particular case, we want to kind of number our carbons that we got going on. And again, we would start up here like an organic, that'd be carbon 1, that would be carbon 2, this would be carbon 3, carbon 4, carbon 5, and this guy down here would be carbon number 6. So one approach is, if you want to, you basically could take this guy and then on the other side of these OHs, if they're not drawn, are hydrogens, by the way. So there are hydrogens on the other side of these guys. Now, if you want, what you could do is just take this guy basically and just drop him down on its side. So you're just going to take it and just drop it over on its side. And if you drop it on its side, you could redraw it if you like, and it will look something like this. When you drop it on the side, 2, 3, 4, 5. And again, if we count all these things, again, that's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Now, when I drop this guy on its side, everybody here on the right-hand side basically goes down, right? So if I did that, everybody on the right just basically goes down. So everybody on the right should end up downward here. So that is OH, that is H, that is OH, and that is H. Everybody on the left-hand side, when you drop it like that, will go up, right? So if it's like that, it'll basically go up. And that will go up. And we can put our guys in here, H, OH, H, and OH. Excuse me. Any questions on that so far? So basically, going to take it and just drop it on the side. So what happens in this case, since this is a hexose, we are going to go with carbon number 5. And if it's not a hexose, typically speaking, it is the last chiral carbon down the road that does this. So carbon number 5 here will actually go and find the carbon-oxygen double bond. And that is what's going to make the ring. And when you do it like this is going to tell you basically what ring you should draw. Should you draw like the cyclohexane ring? Should you draw the cyclopentane ring? How do you do that? You basically just count up the carbons involved in what I just drew an arrow. So that's involved. That's 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. So we are going to need that 5 carbon ring, which is really like the cyclohexane ring. So right off the bat, once you figure out what ring you should draw, you're pretty much almost there. So you just draw your ring. In this case. Remember, it is not a 6 carbon ring. It does have that oxygen that's in there. Now, as we just talked about a second ago, carbon number 6, which is this group, will always end up to the left of the oxygen above the ring. So the next thing you should do is just put that guy right there because that's where he'll always end up. Also good to put that guy right there because now you could use him to number all the other carbons. So this is carbon number 6, and if I come down, that would be carbon number 5. I'm actually going to go counterclockwise here, away from the oxygen. This is going to be carbon 4, carbon 3, if I could count, carbon 2, and carbon 1 in this case. Any questions on that? All right, so what is left is this. We skip carbon number 5 because carbon number 5 and carbon number 1 is basically this mess over here. That's how that all comes together. That's how the oxygen gets in the ring at carbon number 5. Some of that oxygen gets incorporated into the ring. So we're going to start with carbon number 4 here. And it is as simple as when I look at my picture above, the OH group on carbon number 4, is it up or down? It is down. So that's what I draw. I put a line there at carbon number 4 and write OH going down. Carbon number 3, my OH group is up. So I go to carbon number 3 and I drop in an OH going upwards. Carbon number 2, my OH is down. Yeah, so I drop that in there. What is left is the last one there, and that is determined based on what you are asked to draw, what anomer is sometimes referred to, either the alpha or beta version of this. Alpha basically means it's going to go down, that last one, if you were asked to draw the alpha. If you were asked to draw the beta, you can probably imagine it is going to go up, that last one. Everything else would be the same here. And if you were going to draw the beta, that last OH there on carbon number 1 would go in the upwards direction. So they usually will tell you, draw the beta anomer or draw the alpha anomer. And that will tell you basically where you put the last kind of OH, either up or down, based on what they tell you. Question on that there. All right, so why don't you try one here? Why don't you do this one? Okay, so let's take a look. I'll start with the first one here. I'm just gonna number my carbons. Remember where my carbonyl group really is carbon number 1. That'd be carbon 2, 3, 4, 5, and 6. Once again, if you want to, if it's easier for you, you can drop it on its side. And basically, if you want to redraw it, and we'll end up with 1, 2, 3, 4, 5, and our CH2OH. Again, here, this would be carbon 1, 2, 3, 4, 5, and 6. Again, when we drop it on its side, everybody on the right-hand side goes down. And if you don't want to redraw it and drop it on the side, all you have to do is remember right-hand side, they go down, left-hand side, they go up, right? So you can do that as well. And we'll put everybody back where they need to be, hopefully here. Once again, in this case, because last chiral carbon, number 5 there in our hexose, it's going to come over and it's going to attack our carbon-oxygen double bond always. And at that point, if you're not sure, you can just count up carbons. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. That again tells you the ring that you need, which is really like the cyclohexane ring. So again, we're going to go with that ring there. As usual, our 6 carbon there, the guy on the bottom will end up to the left of that oxygen that gets incorporated into the ring. We'll use that for numbering purposes, as that will be carbon 6. This would be carbon 5 going counterclockwise. 4, 3, 2, and 1. Any questions on that there? At this point, all that's left is really just to put in our guys either up or down. Once again, we do skip 5, as that is where the sort of incorporation, the ring closes. So we go number 4, the OH group is down. So we're just going to draw a line in the OH. We go number 3 there, the OH group is up. So we'll go up. Number 2, the OH group is also up. And by the way, on the other end of these lines are the hydrogens. Usually it's left off so it doesn't get so crowded with stuff kind of drawn on there. But there is still, these hydrogens, on the other side of the line and stuff like that. Here we want to do the alpha, and alpha means that it should go down there, our last one. Any questions on that there? Then let's take a look at the other one, which is a little bit different. This obviously is an aldose here. So we have that aldehyde group up on top. The second one that you're asked to draw here is actually a ketose. So we have the ketone group. We still number the same way. We don't start with the carbon-oxygen double bond, but the one above it will be carbon number 1. That will give this guy really the lowest number of 2. This would be carbon 3, 4, 5, and 6. Once again, if you want to drop it on its side, you can. And in this case, you will end up with a CH2OH. You'll also have a carbon-oxygen double bond. And then we got 1, 2, 3, and our CH2OH. Once again, renumbering here, 1, 2, 3, 4, 5, and 6 here. Same deal. Everybody on the right goes down. Everybody on the left goes up. So that's going to give us here an H, and an OH, and then opposite up on top here as we go this way. In this particular case, it is going to be carbon number 5, since this is a hexose, our last chirocarbon. It's going to go all the way over to the carbon-oxygen double bond at the second carbon. Again, that is always where the ring basically forms, through that carbon-oxygen double bond and one of those OH groups down there. And that means that if we count up what's going on, we have 1 carbon, 2 carbons, 3 carbons, and actually only 4 carbons that are part of the ring. That means that we actually need the other ring here, that cyclopentane ring, because we really have only 4 carbons. So we really actually need this guy here in this case, right? That also means that if we look at it, we actually have, unlike the previous one, we have one thing that's off the ring like normal, but we also have another guy that's off the ring. So we have those 2 carbons that are not incorporated into the ring in this case. Question on that? You still approach it the same way. We still know that this 6 carbon here is going to go to the left of that oxygen. So that's where we're going to put it. So we're going to put it the exact same way. So we're going to go a little line up here and go as CH2OH. That is carbon number 6. We'll still do the same thing. That would make this carbon number 5. That would make this carbon number 4, this carbon number 3, and carbon number 2 in this case. Carbon number 1 is off the ring, right? So it's going to be attached there, off the ring. It's not part of the ring in this case. We will still skip number 5 because that's where it comes together to make the ring. So we'll go to number 4 and we see our OH group is up. We go to number 3 and we see our OH group is down. And now we were going to draw, I believe, the beta, I said, if I'm not mistaken. So that means that the last OH should go up. I am still missing something, right? What should go on the other end of that OH? It is this group right here, right, that we left off. So again, that last carbon will find itself off of the ring right there, yeah? Now, if we did the alpha, it would be exactly the same, except that last one would just flip around, and the carbon would go up, and the OH would go down in that particular case. Or if we did the alpha, if we did that way. Question on that one here. All right, so what happens if we actually had a ring type of guy and we wanted to open it up and draw it straight for him here? So if we took a look at one here and we'll just randomly draw something here, let's go with this. And we'll do this. We'll do that. Why not? We'll do this. We'll do this. And we'll do this. And let's just say we wanted to draw, I don't know, we'll do D. Why not? We want to draw the D isomer of this guy when this thing opens up. So we could do it just kind of working backwards from the structure we have. So obviously we have a ring structure here, or a cyclic structure. And one of the first things we could do is really just count up how many carbons we got going on. So that we know is always carbon 6. That's going to be 5. That's going to be 4. That's going to be 3. That's going to be 2. And that's going to be 1 in this case. So we know we have a 6 carbon monosaccharide. We also should probably know, is it an aldose or a ketose? This is going to be probably a aldose, right? Because as we just saw in the previous one, in our ketose, what else ends up outside of the ring? We end up with a carbon group outside the ring over there. And in this case, there is no carbon group. All the carbons are within the ring, and that would imply that this is going to be an aldose up on top. So we got most of the structure already done in a sense. We know we have the aldose group up on top, and we got 2, 3, 4, 5. We know our number 6 guy there is going to be on the bottom, and we can number everybody 1, 2, 3, 4, 5, and 6. Any questions on that so far? Well, we're going to do our normal thing. We're going to, in this case, kind of skip 5, and we could work our way from the top down or bottom up, but skipping 5. So in this case, at carbon number 2, our OH group is up. And when we drop something on his side, the guy that ends up is on the left-hand side. Yeah, so that means that here my OH group is going to be on the left, right? Because it ends up basically. My number 3 also is up, which means my OH group is going to be on the left as well. When I get to number 4, my OH group is down, right? And that means it started on the right-hand side. When you drop it on this side, it went down. And that would be my OH group there. Now, my very last guy there, which is my last chiral carbon, the OH group should go on which side? D means right. Yeah. So again, kind of like when they tell you alpha or beta, they'll tell you draw the D or draw the L, and that's where you put your last one, where that kind of 5th carbon comes into play. Any questions on how to go backwards there? Or forwards or backwards? All right, so why don't you go and draw one opened up? Why not? Why don't we just do this one here? Counting up all the carbons you got going on outside the ring, including the ring, is a good idea. So that's a carbon there. That's 1, that's 2, that's 3, that's 4, that's 5, and that's 6. So I know I got a 6 carbon monosaccharide happening. In this particular case, you could also number them if you like as well, the same way. So we know going counterclockwise, we go big number to small. So 6, 5, 4, 3, 2, and once again here, our carbon is going to be off of the ring, which would be number 1. I also know that I see here 2 things that are off the ring, so that probably implies that this is going to be a ketose, right? So that's where that kind of happens a lot of times. You got a couple of carbons off of it. So I could kind of draw my structure here. I got carbon, carbon, oxygen, double bond. That's going to be my ketone group. And then we just kind of continue on 4, 5, and then obviously this group here. Once again, we do want to count from the top down, closest to the carbon oxygen double bond to give a small number. So that would be 3, that would be 4, 5, and 6. That means here, a carbon number 1, that is going to go up here in this case, yeah? At this point, we have carbon number 4. And carbon number 4 here, we have the OH down, which means it was on the right-hand side as when it dropped down, right to the right. Carbon number 3, we also have it down, which means it should be to the right. And that leaves us our carbon number 5, which in this case will be determined by this, which is L, which means we will lay it up there on the left. Yeah. Any questions on that there? So these carbohydrates will go into these sort of cyclic forms. They actually will open up and close a few times along the way. And, depending on sort of which form as they go to either our sort of D or alpha or beta sort of form. Any questions on that there? All right, we'll lay that up for today.